So again, very welcome to the last 2 hours in CFD. That's the 25th lecture in CFD. And today, what we're going to do is, in the first hour, I will present the results of the project. Of course, it's not fully ideal because many of you may not have done the project yet. But in that case, it just serves as a demonstration of what you should get. And I'll try to add a little bit more about the physics and kind of the expected behavior that you should get, and maybe also the reasoning why you would get a certain behavior. That's in the first part, and then in the second part of the first hour, I'll also have a few more slides, which are perhaps a little bit more interesting when it comes to the history of CFD and what where all these things that we discussed now during the course actually came from, and also that may serve kind of as an hopefully interesting conclusion of the course. In the second hour, we will then have the usual homework review together with Luca and Fermin, and they will discuss mainly homework number 6, so the one with the finite volume discretization. Of course, I'll be happy to answer any questions that you may have that you would like to discuss with me, either on the project or anything else. And as I said already last time, if you have any more questions later on, you can always contact me or Ardashir or Luca and Fermin. Perhaps the easiest way in is to ask Luca and Fermin first, and if they then think that they wouldn't or cannot answer, then of course I'm very interested. Exam preparation, you can base that on all the material that we have gone through during the course, including also the study questions that are on Canvas. The questions during the exam will be similar to those questions. Okay, but with this said, I would like to now start to look at the project, or discuss the outcome of the project. So let's see. So as you know, the basic idea was to do the lid-driven cavity. The lid-driven cavity is a standard case. We mentioned that it's a very popular case for doing validation of CFD codes, because you can quite simply treat it as a two-dimensional case. So you don't necessarily need to look at a three-dimensional case as shown here. You can just take a vertical slab through that domain and then treat it as a two-dimensional case, which would essentially correspond to a very wide box in 3D, where you then could expect to have two-dimensional conditions in the center plane. Now, we're doing numerical simulations here in this course, of course, but there is also the possibility to do experiments. And there is one experiment in the literature where they tried to match experimental studies and DNS. DNS here stands for direct numerical simulations, so simulations without turbulence models. And you can see here the setup that was done in this experiment, where you have on the right side or the left side, so figure A, you have the numerical setup, which it's, as I said, just a three-dimensional extension of our two-dimensional domain. You can also directly see from this is that there is no external boundaries, in the sense that you don't have free stream boundaries, you don't have inflow, you don't have outflow, which makes it very suitable for numerical simulations. Sub panel B shows you the experimental setup, which is slightly more complicated because you need to somehow get the velocity, or you need to drive the flow with this belt on top. You can see how this is done in the construction. You essentially just have two wheels, and then you have a belt between them, which then forces the flow. And the observations are done, or may be done, using PIV. That's the system that is shown here, where you have a laser sheet, the green bit in this plot, which you use to illuminate the flow and particles in the flow. And then you have a camera, which is more or less orthogonal to that, which observes then the motion of particles which are inside or which are illuminated by the laser sheet. And by tracking those particle traces, you can then deduce what the velocity was. And the video that we have already looked at during the introduction, I can just show it once more. It's essentially like this. This is the experimental setup by Lieberson. And you see here the laser sheet, the green thing, the cameras, and now they will. You see it also the lid on top. And if you now zoom in, you see this the cavity. That's this little square on top. And now I think the focus changes very soon. It's a little bit. Now you start to see it. You see here how this this vortex or kind of a rotational flow is induced inside the cavity. As I said, this is what we would like to study. Based on the discussion that we had earlier, let's just go on here. So this was the case that we look at. Square box. Everything is at rest except the upper wall, and we start with an initial condition with a fluid at rest. As you know, for the second part, we also include the temperature. For the Rayleigh-Benard case, we include the temperature. That's why I have already included also for the results I'm going to show you now, I've included the temperature also for the lid-driven cavity. And it's included in that way that I have a constant temperature on top and a constant temperature on the bottom, and on the side walls I have adiabatic condition. That will be exactly the same as for the Rayleigh-Benard convection. It actually turns out, we will see that in a second also, that the inclusion of the temperature on its own serves as a nice way of visualizing how the motion of the flow is actually happening. And that's maybe also something that you can keep in mind if you want to post-process simulation data or visualize simulation data. You always need to think, what is it actually that you would like to show? What is the main physical concept that you would like to evaluate or demonstrate or understand? And then you can find quantities that you then extract that can support your hypothesis or the type of results that you want. In this case, I feel it's kind of an interesting thing to see how the fluid from the top actually comes to the bottom by means of this vertical motion, and therefore the temperature serves as a nice indicator of how this mixing takes place. So you will see that later, that at times including a passive scalar into a flow may be a good idea just for visualization purposes. But anyway, this is the setup, and if you now just start to look at some of the results, as we discussed earlier, there is just one dynamical parameter that describes the flow case if you assume that we have a square cavity, and that is the Reynolds number. So everything we can encode with the Reynolds number, because the Reynolds number is based on the belt velocity. That's the only velocity scale that we give in. It's based on the height, which is h, and it's of course based on the fluid property, which is the viscosity. So everything that you need to know about the square lid-driven cavity is encoded in the Reynolds number. So that means the only thing that we need to change is the Reynolds number. Typically, we start. Here we start with Reynolds number 100, which is perhaps also the Reynolds number that you may want to start when developing the code, because it's somewhere intermediate between very low Reynolds numbers, where the flow is extremely boring, and very high Reynolds numbers, where the flow is quite demanding in terms of resolution. So 100 to me is kind of a good compromise, where you still have effects of both inertia and effects of, well, not too much inertia, so you still have the viscosity being present. But let's look now at what happens. Just to remind you again, I think I can. So the idea is you have the lid velocity like this. So on the left side you have the velocity. You have the lid velocity like this. dark blue means it's at rest. So that's the initial condition. Of course, then the idea would be that we would expect a vortex to develop that looks like that. Okay, so let's see what happens. Well, this is now the velocity, the velocity amplitude in colors, and then you see small arrows which give you the velocity direction. And what you see, it was maybe a bit quick, but what happened is that, of course, up here, the velocity directly goes to velocity amplitude number or equal to 1, which is the lid velocity. And then you see that here the flow is accelerated. You see a boundary layer growing along the upper wall. As you know, a boundary layer is kind of growing when you go downstream, and that's what you see here, that this thickness here is increasing. Then, of course, comes a problem because there's a wall here, so the flow cannot continue here. So the flow is then deflected around the wall, downwards, I should say. Downwards, there is no additional forcing of the flow anymore because the sidewall here is at rest. So that means there is no further acceleration of the flow. The boundary layer is not really growing anymore. The flow separates from the wall and then kind of goes back like this. So this is kind of what you would get. You also see that this vortex doesn't reach fully down in all the corners because the viscosity is too large or the velocity is too small to essentially get mixing here in these corners. These corners are still at rest. Also, you see that there's a center of the vortex, which is there in the middle, which is also characterized by having essentially a zero velocity because you have the velocity, the fluid rotating around this center, but the center is actually still. So this is what you would get for this intermediate Reynolds number. Intermediate again means that you have a quite high viscosity, but you still have some inertia that you get actually the flow to move in that way. Inertia or nonlinearity here also means that the flow field is slightly asymmetric, so there is no symmetry with respect to this vertical line. So this side looks different from that side, and that is the effect of or the result of the nonlinearity. I was saying before that at times the temperature is a good indicator of how this mixing happens, and let's just see what the temperature does. Well, you see that it's perhaps slightly boring, I don't know, but you see that the blue temperature, which I impose here, in the case for the lid-driven cavity, it doesn't matter whether blue would indicate high or low temperature because it's linear in the sense that you could rescale the temperature with a factor of -1, so you could switch it in principle. But anyway, the blue temperature is then, of course, transported with the fluid around this corner. So you see that there's a region of low temperature, blue temperature along this sidewall, which just comes from the fact that it's transported down. And then, of course, accordingly, you have a region of kind of red temperature that's being pushed up on the other side. So you can see that there is some temperature, a new temperature distribution where you have blue going down and red going up. And of course, that's kind of what you would also expect to happen. But at the same time, you also see that there is enough diffusion present so that it's not that the blue temperature would reach all the way down to the lower wall, because essentially the effect of, or the temperature gradient is then diffused. Okay, so this was the intermediate case, and as I said, I would recommend perhaps to start with this case also in your development, because it has effects both of inertia but also effects of high viscosity. Now let's go on and look at another case. which is the lowest Reynolds number case, or lower Reynolds number case. I pick here Reynolds 10. You can pick a lower Reynolds number if you want, but if you pick a lower Reynolds number, then you will see that, well, what would you see? I guess we can maybe talk about that afterwards, because if I just run this very quickly, so the velocity field looks like this, and the temperature field looks like this. Now, what have you seen here? The speed of the video is exactly the same as on the previous for Reynolds 100. But what you have seen is that the adaptation was extremely quick. And of course, the reason for that is because the Reynolds number is lower. So your time scale, the viscous time scale, has become much smaller. Because, as you remember, this relates to the viscous limit, the viscous time step limit, which then reduces your time step considerably. And that is a problem that one has for low Reynolds number flows if we treat them with this explicit time stepping that we have in our code. So the time scales get much quicker, which also means that maybe you don't want to go down in Reynolds number too much if you still want to integrate up to the same non-dimensional time as we did for the Reynolds 100 case. So that was one observation. Time scales get much quicker. The other thing, which I believe is quite interesting, is that the velocity field has become symmetric now, or more or less symmetric. So the left side and the right side, they are essentially the same. I mean, mirror symmetric with respect to this slide. And this is a typical result that you would get for Stokes flow, for a flow where the inertial term can be neglected, the nonlinear term can be neglected. Because then once you are in the Stokes limit, then you will realize that the equations are becoming linear, and you can then impose an exact symmetry along those lines if that is permitted by the boundary conditions. And for the velocity field, this symmetry is also in the boundary conditions. In the temperature field, this is not the case because we have symmetry breaking due to the boundary conditions. But for the velocity field, it is like that. And that is also a good test, I guess, for your code development. If you go to the lower Reynolds number limit, you should get something that is more and more symmetric. So faster timescales and symmetrical flow field. And of course, also you see that because the viscosity is larger, this the flow doesn't reach, or the velocity doesn't reach as far down as it has for Reynolds 100. Okay. Then if you go in the other direction, so we actually go to higher Reynolds numbers. Now I directly do the step from Reynolds 100 to 8,000. Of course, you can have a number of steps in between if you wish. But at Reynolds 8,000, you will actually expect that the inertia is much more dominant. So the convection part is much more dominant. Whereas the diffusion is not as relevant any longer. Let's just see what happens. If we start the velocity field first, you will kind of see this behavior. So you can see a very thin boundary layer here on top. The boundary layer thickness is also dependent on the Reynolds number, and if the Reynolds number goes up, the boundary layer thickness goes lower. You'll then see that the flow is again pushed down along the sidewall. Also here, a very thin boundary layer developing, and then the kind of the flow goes around nearly in a circular way. You can also see, if you look carefully, that there is some secondary vortices. So if this vortex is going in this direction, then you will have some secondary vortices in the corners that are being driven by this main vortex. I guess there would be even one on top. So this is the typical way that a high Reynolds number flow would look like: thin boundary layers, a lot of unsteadiness. So it will take a long time until you actually reach a steady behavior. Also, what you maybe you cannot see it. Well, maybe you can see it. I also needed many more grid points here compared to the previous plot, which was for the lower Reynolds number, where the spacing between the grid points was much larger. Here, I need many more grid points in order to be able to resolve all the flow structures. Now, so if I just plot that again, just to mention again, there's a lot of unsteadiness. It takes a long time until the flow actually settles down. Also here, maybe I can make a comment. People have studied this flow case of the lid-driven cavity using methods of stability analysis, and they have concluded that the Reynolds number above which the flow would never become steady, so it will always be unstable, is on the order of 8,000. It depends a little bit on how you treat those corners here, which I have mentioned also before as one critical aspect, because you need to be a little bit careful with these corners in order to fulfill, to be convergence and fulfill continuity. But the critical Reynolds number is somewhere around this 8,000. Okay, let's look at the temperature field as well. And I think that's actually the nicest plot that I will show you today, because here you really see how the mixing is taking place. You really see how the velocity picks up blue colored fluid from the top and kind of tries to mix it. Look like this. You get a nice vortex that is generated of the blue flow, which is then mixing in the whole domain. And you see that it also reaches very far down in the cavity. It's maybe only in these corners where the cold fluid has not reached. Also, I guess you can directly imagine that the heat transfer, if you would now measure, how much heat from here would go up, so the heat flux through this cavity is much larger for the high Reynolds number case than it was for the low Reynolds number case. So if you now imagine if you're an engineer and you would like to build this as a device to transfer heat from, imagine that you have an engine here, and this would be your cooling device. Then of course you would like to cool it with this turbulent flow, because you certainly have more heat flux through the cavity. Of course, at the expense of perhaps needing to add more energy here in the lid to get the whole thing running. Yeah, let's just watch this again because I like it. So you can really see how you get this vortex arising. Okay. Well, that essentially were the three different Reynolds numbers for the lid-driven cavity, with the main features that you should also see in your results. Now, there's a few more things that I can mention. So for instance, you can kind of check whether the flow has become steady. This is the same plot as we had for Reynolds 100. Looks like this. But if you now track a probe in the middle of the cavity, you can see that the value in the middle of the cavity first rises, the velocity, and then at some point it becomes steady or doesn't change anymore. And plots like this you can then use to determine whether or not your flow has actually become steady. So imagine if you kind of try to make the difference between this point and this point, and you plot this as a function of time, you will see how this error, let's say the unsteadiness, will go down more and more. Yeah, this is again just a kind of a summary of what you would how the flow would look like as you increase the Reynolds number. And it's really this type of behavior which clearly indicates the influence of Reynolds number, or as I was saying, the only bifurcation parameter in this case. Okay, Let me now move on in my discussion to the second flow case that we have. Unless, of course, you have any question, which you can, of course, ask at any time. So for the Rayleigh-Benard convection, if you remember, the idea was we have two solid walls, and we have temperature difference, and then you get these convection cells building up. And these convection cells build up once you are in this unstable region, the green region here, which is a function of the Rayleigh number, as we have discussed, and the wave number. So this distance or this length here would be 2 pi divided by this k. That's the wave number of the disturbance. And as you also can see, there is critical Rayleigh number and wave number, which is at 1703 or 1708, and roughly pi. This is more or less pi, meaning that these convection cells, they're roughly circular. But now the question is, okay, what does our code do? Can we actually reproduce that? And also here I have a few videos which we can now go through one after each other to kind of see whether we actually get the right result. So first, what you can see here is that we have not a square cavity anymore, but we made it much longer than it is high. So we have we do that in order to imitate periodic boundary conditions, which we would actually need. And then also what you can see here at the initial condition, we put a little bit of noise on the solution to make sure that stuff starts to happen. The noise is of very low amplitude, so it's not much noise that we put. So it's on the order of 1% or so of the velocity. But now let's see what happens, and then we can discuss a little bit more. There was a question on the chat whether this part is only for PhD students. Yes, this part is only for PhD students, but of course, if you're interested, I think it's a very interesting case to look at, and it's not so much more work. So if you want, then you can do that, but it is only for PhD students. Yes. So let's see. This is at the Rayleigh number of 2,700. If you go back, 2,700 would be somewhere here. So there is a bit that is unstable. Okay, let's see. Temperature field, velocity field. You can see there is an unsteady behavior. It takes a while until the flow has adapted. But then at some point you see that it becomes actually steady. And now at time 20, it has become steady. And you see, well, there is a kind of a wavy-like modulation of the temperature, meaning that you have high velocity, so high temperature is being pushed up, and here low temperature is being pushed down. So that means essentially here you have one vortex, and here of course you have the same in the opposite direction, and so on. So you actually see here some of these some of these convection cells. So that means indeed it seems that the flow has actually become unsteady here. In the velocity, you see the same. You have high velocity here, low velocity here. So that means you have a vortex that probably looks like this. And of course, if you now correlate it, you see that this is, of course, exactly the case. So Reynolds 2700 is clearly unstable, which is what the stability diagram also predicts. Now the question is, what happens if we start to increase the Rayleigh number, which, as we said earlier, this would be very similar to the Reynolds number as in the, by analogy. It means that you have less viscosity, more convection. Do that. You see, it also happens very quickly, but the shape of these convection cells has changed, and actually it becomes. They kind of look like, they look like this. And that's, well, I'm trying to draw something. they kind of look like mushrooms. You know, one mushroom like this, and then you have another mushroom that is kind of upside down, and so on. So these convection cells, they are not sinusoidal anymore, but mushroom-like, and this is a typical phenomena of convection flows. That you get these mushroom-like shaped structures. Just think of you know, atomic bombs where you have different things, although it's not exactly the same effect there. So this was for the temperature, and of course for the velocity you kind of see the same behavior. Another thing that you can directly see is that there is of course an effect of the side walls here, but in the middle you then see that the flow has actually become quite developed in the x direction. Okay, so this was for the highest Rayleigh number. And now the question, now we would like to hunt this the critical Rayleigh number. We want to see whether our code can actually do that. So I have now here a Rayleigh number of 1715. If you remember, this is slightly above the critical Rayleigh number. The critical Rayleigh number was 1708, so that means it's a little bit higher. Now we can see what happens. Well, it happens not much. It's very slow. But if you just see here the pattern, you see that there is actually some instability present. Same thing in the velocity. You see it takes a long time until it develops. You see so clearly that there is some effects of the sidewalls, but then in the middle we are somewhat homogeneous or fully developed in X. But after a long time, you see that the velocity amplitude seems to, well, stationary or even grow a little bit. So that means there's clearly an instability present. The flow is not going to decay to zero. There is something happening. That means this one is actually unstable. So at 1715 Rayleigh number, we are unstable. Okay, I don't show you the video for 1700 because the video is a little bit boring. It would just decay. But if you trust me, the above velocity field here or temperature field is actually from 1700, which means that at that point it was stable. So that means we have actually a code that could show that from Rayleigh number of 1700 to 1715, it has become unstable. And again, remember, the critical Rayleigh number was at 1708. So our code could, in fact, reproduce that result, which is quite a cool thing. It's these type of analytical results that you can reproduce with your simulation that can be used to validate your implementation to make sure that your code is actually doing the right thing. So in this case, we could validate our code with this stability result. And of course, that's a very good thing. And then I guess the rest here is what we have discussed. You can see that the nonlinearity, the increasing nonlinearity with the increasing Rayleigh number starts to change the kind of the shape of these waves. And then you get this mushroom shaped stuff at the highest rate. Now, I would just like to also show you another two more videos for Rayleigh-Benard. One is a video that I stole from Wikipedia, which is an illustration of where Rayleigh-Benard convection also happens in nature. I have to be honest that this is actually not Rayleigh-Benard convection. It's Maragoni convection, because the boundary condition on top is actually not a solid wall, but rather a free surface. So it's the stress distribution is slightly different, but the basic Maragoni and the Rayleigh-Benard convection is actually very similar. You heat from the bottom. This is, I mean, imagine that this is a casserole or a frying pan, which you heat from the bottom, and then you get again these type of convection cells. But of course, in this case, it's now three-dimensional, and it doesn't play. It says the codec is unavailable. Okay, that's a little bit sad, but well, somehow I guess you can you can imagine what it would be. It would just form now in 3D these type of blobs or convection cells in 3D. In fact, if you control them very carefully, they would look something like that. So there will be hexagonal shapes that will be there. So you will get a very nice array of with six corners if you control them very carefully. Okay, so this was an experiment or a video, but now also something else that we did a few years ago with in a project course. We just implemented Rally-Binar convection in one of our simulation codes, not a MATLAB code, a Fortran code, which is much more efficient. And in this code, we ran Rally-Binar convection in 3D with a higher Rally number of 10,000. We used a Prandtl number of 0.71, which corresponds to air. And if I just play that, you can see what happens. You again see these three-dimensional convection patterns. Red velocity is high, low velocity is blue. You can see that these structures emerge. Actually, it turns out that this will remain unsteady for a long time. Depending a little bit on the initial conditions, you either get these hexagonal structures, which I think there was one that you could see somewhere, maybe here and here. Well, now of course they're gone. Or you can also get span-wise or stream-wise rollers instead of these three-dimensional ones, depending a little bit on how you choose the initial conditions. Okay. Yeah, so this is essentially what I wanted to show you about the project and the results of the project. Do you have any questions or something that you wonder about? Because if not, I have a few more slides that relates to how you could, continue doing CFD or deepen your knowledge. So first of all, I would like to mention that we at KTH Engineering Mechanics, we are very interested in fluid mechanics or CFD in general, in particular also in the context of something that is called the Swedish eScience Research Center, which is one of the strategic research areas originally funded by the Swedish government. And within this Swedish eScience Research Center, there's actually a lot of fluid mechanics going on. Just show you two examples that we did in our group. So for instance, in this 5 years report, we highlight this one case, which is a turbulent flow in a torus, or also something like that, which is the turbulent flow developing on a wing surface. So it's these type of simulations that we do quite a lot at Mechanics. But of course, there's many other simulations that we do if you're interested maybe for some project work. And that's maybe the last two things that I would like to mention regarding that. So if you want to continue, there is the possibility to do master thesis work with us. That's I guess it's 30 credits, which then lasts for 5-6 months. And sometimes we can manage to get journal papers out of the master thesis. I'm just having here two examples of papers that we could publish based on a master thesis. So in this case, it was Lawrence, and in this case, it was Srinivasan that could do Prem Srinivasan that could do a nice journal publication. If you don't want to directly go for a master thesis, there's also this project course, which I think now the course number is not mentioned, but it's SG 2010, which is a slightly smaller project that you can do, which only gives you 15 credits. If you're interested, one can certainly find a nice project. The final point regarding this is for the CFD course is also that there will be a course evaluation, which I will send around online at the time of the exam, because there's also some questions relating to the exam. So I think it would be good if you have seen the exam before you fill that in. So please fill that in, and the more you tell us what you liked or what you didn't like, the better it is. In particular, now in this time when the course was actually given online, which is for the CFD course the first time that we did it. So let me know what you think of the course, and of course, if you have more feedback that you would give to me or anything about the course, just talk to me via email. Now, we have 4 more minutes for the course. And if you don't have any comments, I would just like to show you a couple of more slides, which could maybe serve as a kind of a conclusion of the course. Because I would like to also show you very quickly, we mentioned that in the first lecture, but now as you know much more at the end, I would just like to mention very briefly, I mean, how this all happened or started with a CFD. And I think if you're interested in history, I think a very interesting book to look at is this book, which is called Weather Prediction by Numerical Process by Louis Fry Richardson, and it was published in 1922. And I would say this is really the first time that somebody was writing about CFD. Not only that, this book is also famous because there is one part which essentially explains what turbulence is all about and why simulations are maybe helpful. It has this famous quote on turbulence: big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity in the molecular sense. So that's essentially the turbulent cascade that we all know about these days. But I have these pictures here which kind of illustrate a little bit on how this turbulent cascade would go on. If you kind of zoom in, you essentially, it looks all the same, it just gets smaller and smaller up to a certain point when viscosity happens. Of course, this then had implications to Louis Fry Richardson's idea of how to do simulations, and he actually did his first simulation using, in 1920, doing a weather forecast of 8 hours. It took him 6 weeks to do this weather forecast, and he used 2,000 computers. Of course, since computers were not invented yet, he used humans, to actually do these calculations. And what he called this was then the so-called forecast factory, where you have a lot of people calculating stuff. Now, he actually also thought about how to do that in practice. And this is a picture or an illustration of the forecast factory by Louis Fry Richardson. And the basic idea is that you have a lot of little rooms where people sit and calculate. And you have one guy here in the middle, which is kind of the master of all of this. And then using spotlights, he could then ask different rooms to tell him what results they got, which they can then project, as you can see here. And then he in the middle can kind of combine that into a final result. The stunning thing of this is that essentially what this illustrates here is the design of a modern computer. Think of it as a cluster, where each room would correspond to one CPU or one core. They calculate stuff, or one node maybe. They calculate things, they talk a little bit between each other, between the neighbors. That would then be kind of the different cores in one node. And then you have message passing, or MPI, between different nodes which are distributed in the network. And that's governed by one master node which kind of controls everything. In the end, this is the design of a modern computer. And that's how we solve CFD problems these days. Okay, I think with this picture, I would like to close the CFD course. So whenever you do CFD, think of the humble beginnings now 100 years ago, how Louis Fry Richardson was imagining how CFD works and compare it with how it is done today. And it turns out it's actually very similar. It's just that the human people in these little rooms are replaced by computers, but the whole idea is very, very similar. Yeah, so with this, I would like to close for the lecture part. And second hour today will be given by Fermin about homework number 6. And yeah, I would like to thank you for participating. If there are questions in the future regarding CFD or some of these master thesis or project works, just contact me, and then we can see what we can do. Other than that, we will meet again during the exam in roughly 2 weeks. Okay, thank you very much.